Dear students, I welcome you for the session 3 of Analog Electronics on Module 4, Feedback and Oscillator Circuits. Myself Nataraj Vijapur, I will be continuing with this session 3. In the previous session, we had started with feedback concepts. In the session 1, we covered feedback concepts. We discussed about general feedback structure. We discussed how feedback alters the properties of open loop amplifier. Okay. We discussed about feedback playing a very major role in with respect to stability of amplifier, input output impedances of amplifiers. These all we discussed in session 1. In session 2, we discussed the variety of ways in which feedback occurs. Okay. So, we discussed about feedback network, how the voltage is being fed back, current being fed back, whether it is being fed back in series or shunt, depending on that. There were 4 connection types we discussed in this feedback connection types. Then session 2, we discussed about practical feedback circuits. We had discussed an example of voltage series feedback amplifier by making use of an op amp as well as a FET circuit. Okay. We had started actually with emitter follower as an example of voltage series feedback. So, we will continue with that. So, today's session we are looking at practical feedback circuits of voltage series feedback configuration, current series feedback configuration, voltage shunt feedback configuration and current shunt feedback configuration. Okay. So, we will be looking at practical circuit for each of these. In the previous sessions, we just looked about the topologies, how the input and output impedance varies, how the different properties vary, we discussed. So, this session we are discussing practical circuits. So, at the end of this session, you will be in a position to analyze any feedback amplifier circuit, and you can design the feedback amplifier. You should be able to design a feedback amplifier depending on the requirements after attending this session. Okay. So, these are the outcomes. Again, for this content, I have referred following textbooks: Robert Boylsted and Louis Neshelski, Electronic Devices and Circuit Theory, Pearson Publications, 10th edition. So, this is a very important book from university point of view, syllabi point of view, analog electronics point of view. Then Adele Cedra and Smith, Microelectronic Circuit Theory and Applications. So, this textbook particularly explains feedback concepts very well. Then next, I have also taken Millman and Halkia's Integrated Electronics, Bakshi and Godse Analog Electronics. So, these all 4 subjects are important. Okay. So, these I have utilized to prepare my content. Okay. So, in the previous session, we discussed about voltage series feedback configuration. Okay. We had also discussed about 2 circuits. One is which makes use of FET and another one which makes use of op amp. So, today I will be discussing about one more example, practical example for voltage series feedback, which is emitter follower. Okay. Let us recall the circuitry. Recall the circuitry of voltage series feedback. So, what all it consists of? A voltage Vs, an open loop amplifier, a feedback network. Okay. So, the input voltage being amplified by the open loop amplifier, output voltage is obtained. This is fed to the feedback network. Feedback network samples, you can say, or collect a part of output voltage. It is actually an attenuator. So, it just collects a part of output voltage and that is mixed in a series with the input voltage to generate a voltage Vi. Okay. So, this is the configuration. I think all of you are noting down this. We are just recalling the concept of voltage series feedback. Now, this actually is being related here to the emitter follower circuitry. We have seen this emitter follower. In fact, you have used it in the earlier sessions. You have studied this, you have worked on it on the emitter follower. Okay. So, emitter follower is one of the 3 configurations. We know that BJT or a transistor amplifier can be biased in common base configuration, common emitter configuration and common collector configuration. In common base configuration, base is made common between emitter and collector. Emitter acts as an input and collector acts as an output. In common emitter configuration, what is being done? Emitter is made common, signal is applied to the base and output is taken from a collector. Both the configurations, common emitter and common base, the output is taken from a collector junction. Collector is a reverse biased junction. You will observe a high output voltage or a voltage gain is high. Now, coming to common collector configuration. Okay. So, this is an example of common collector configuration. You have an input voltage Vs being applied between base. Okay. So, here what you can observe is the common collector configuration. Collector is made common with respect to VCC, supply is being, collector is being connected to VCC, the output is taken from emitter terminal. The moment output is taken from emitter terminal, it is common emitter configuration. We know that base to emitter junction is forward biased for transistor operation. Okay. So, when you forward bias it and you take an output, this junction will have a less resistance. Obviously, voltage gain will be less than the one maximum possible is 1. So, output waveform resembles input waveform. So, it is also called as emitter follower circuitry. Okay. So, you have base to emitter junction forward biased by a resistance RB, collector to base junction is reverse biased by supply and the RC. Okay. So, Vs is the source, it generates an input voltage Vi between base and emitter terminals, output is taken across the resistance Re here. So, that is Re, the output voltage. The important point what we can note here is this Re acts as a feedback resistor. Okay. It is common to input loop as well as it is common to output loop. So, it is a feedback element here. Okay. And previously we discussed in stability analysis also, like in the earlier chapters, Re provides the stability. Okay. So, when Re there we have seen that Re protects, it protects Q point against variations in temperature. Okay. So, now here it is playing a major role, that the role of it providing stability against temperature here is analyzed from feedback point of view. Okay. So, this is the circuitry. So, how the circuitry works here? How actually you can have a feedback which ensures stability? You can observe here that so, when the input voltage is applied to it, the input AC signal is applied to the transistor, it amplifies the AC signal, output is obtained. The output voltage appears as Vf here across Re. If due to variations in the load or because of temperature, because of some parameters, external parameters, if collector current increases, then the emitter current increases. So, feedback voltage Vf also increases. If feedback voltage Vf increases, this is at the emitter terminal Ve. So, what will happen to Ve? So, its voltage will increase, Ve will increase or Vbe will come down, or Vbe is in the sense instantaneous Vbe is nothing but input voltage for the transistor. So, input voltage is reduced, which in turn reduces input current, and obviously collector current will be reduced or output will be brought back to its original value. That is how Re plays a very important role in the stability of an amplifier. Okay. So, we have to analyze this circuitry, we have to analyze this voltage series feedback emitter follower circuitry. So, first thing you have to determine here gain of the amplifier, of the transistor. Okay. So, gain A I can express here. Now, the feedback is part of the circuitry only here. So, open loop gain can be put as output voltage, which is V naught, divided by Vs, the input voltage. Output voltage, how can you express? Output voltage can be expressed as output current into output resistance. Now, here output current. So, which current is flowing here? IE. We are collecting output across emitter. We are connecting output across emitter. So, the IE current will be flowing here. We know that IE and IC are nearly same. By H parameter model, I can call IC as HFE into IB, which in turn is equal to IE. So, it is IERE, which is HFE IBRE divided by Vs, which is the input voltage. That is further equal to HFE into RE. Further, IB can be put as Vs divided by HIE. Okay. So, now you can think why this Vs divided by HIE is coming. Okay. So, if we look at H parameter model, the H parameter of this common emitter configuration. Okay. If we draw the H parameter of this CE configuration, I can replace the transistor. So, how to draw the AC equivalent circuit? To draw the AC equivalent circuit, initially DC voltages are set to 0, only AC voltages are being taken into considerations. So, in that case RB will be connected to ground, HIE. So, this is the current IB which will be flowing into the transistor. Then we have RE, HFE IB, right. Then we have RC being grounded, and you are taking output voltage across the emitter, right. So, now this IB can be put as, this is the supply voltage Vs. So, I can put Vs IB as Vs divided by HIE. So, I can substitute Vs divided by HIE. If there is no feedback, okay, if there is no feedback being taken into consideration, then the circuitry will be without this RE. Okay. This will be your transistor, which is an open loop amplifier. Okay. So, now what we have discussed is how the IB has come, how this base current IB you have substituted. So, you can substitute it as Vs divided by HIE. Further, after simplification, Vs gets cancelled. So, it will be HFE into RE divided by HIE. Okay. So, you have the open loop gain. Further, feedback network beta, how you can get the feedback network beta? Beta is Vf divided by V naught. So, feedback here you can observe from the diagram. So, you have an output voltage being obtained here, beta is equals to Vf divided by V naught, which is equal to 1. So, I can express the closed loop gain or gain with feedback AF as AF equal to V naught by Vs, which is equal to, we know that we have already determined that for the feedback configuration closed loop gain will be A divided by 1 plus A into beta. So, substitute and you will get the expression for closed loop gain AF. Okay. So, which is HFE RE divided, the whole divided by HIE plus HFE RE. Okay. So, this is how we analyze voltage series feedback emitter follower. But what is the point to be carried here? Point to be carried here is RE. This RE provides stability. Okay, it improves the input impedance. Okay, it also serves to control the gain. Okay, then next, so in effect we discussed about 3 circuits now: voltage series feedback with FET, voltage series feedback with op amp, and now voltage series feedback with emitter follower. We will proceed further to current series feedback, the next topology. Okay, so here we are going to discuss how the current feedback will help you. Okay, so now here recall this session, recall the previous session we discussed about current series feedback topology. It consists of an amplifier A, a feedback network beta, a input voltage source Vs, okay, then you have a load impedance RL. Okay, so now we have to analyze here. So what is being done here? You have an amplifier of which type? So this amplifier is called as transconductance amplifier because it accepts input voltage and generates an output current in proportion to the input voltage Vi. So this being open loop gain of this amplifier is put as I0 divided by Vi. So this is the input voltage Vs. The load current generated is fed back in series to the feedback network here. Okay, so you are sensing the feedback current via feedback network. So this feedback network generates the output voltage depending on the input current it receives. So I0 is the input current for this feedback network, and it generates an output voltage Vf which is equal to beta into I0. This is mixed in series with the input voltage Vs. So it generates an voltage Vi. Okay, so this is about current series feedback topology. So we have discussed this. Let us continue further. Let us look at one practical circuitry which makes use of this current series feedback. Okay, so this is a well known example. All of us, we have used it in the previous sessions. This is the most popular configuration of BJT. It is common emitter configuration. Okay, so here transistor is connected in a common emitter configuration. So what all it consists of? It consists of sinusoidal AC source Vs, which is the signal to be amplified, a coupling capacitor C1 which blocks DC and allows only AC. Now it is a which mode of a transistor? It is CE configuration, where emitter is made common between base and collector. Okay, so the input voltage appears between base and emitter here. Okay, supply VCC along with RB forward biases the base to emitter junction. VCC along with RC forward reverse biases the collector to base junction. Right. So you have again important element, a resistor RE, which provides stability, which provides protection against temperature, or Q point, what we have analyzed previously. Now in the voltage series feedback we discussed about emitter follower circuitry because the voltage was taken across the emitter. Now the voltage is taken across the collector. So it is a common emitter configuration. Base is input and collector is output. Okay, so you can observe the diagram, you can take down this diagram. Okay, so supplies Vs, input coupling capacitor, RB, RE and RC, VCC. So you can copy this diagram. So what is important is output is taken across the collector. Now can you visualize how the feedback happens here? Okay, so the feedback happens here via resistance Re. So this Re is common to the input loop as well as RE is common to the output loop. So, RE is present in both input loop and output loop. So, it is a common element which helps you to achieve the stability. Okay. You have input voltage Vi, which is generated because of the input voltage. Now, the output voltage here, the voltage drop which appears across RE acts as a feedback voltage here. It acts as a feedback voltage of Vf. So, how again the circuitry works? Very simple here. So, if at all due to some parameter, some variation, if output current increases, so this is a output current, right, which is flowing IC here and it is IE here. So, if this current increases, voltage Vf increases. If voltage Vf increases, the effective input voltage, which is VB minus VE, it decreases, which decreases IB, input current. If IB decreases, IC will correspondingly decrease. So, here I am talking about instantaneous currents. Okay. So, this is how the feedback happens, and the Q point may be maintained or the stability may be also maintained if it is an operation with the AC signal. Okay. So, this feedback ensures the removal of noise, removal of distortions, improves the linearity in the operation also. Okay, fine. So, the same aspect is being explained here. It is this transistor amplifier you have used in many circuits. CE configuration you will find in all of the circuits. The moment RE comes, it is nothing but the feedback, and you are taking output across collector. Okay, fine. So, this is an example of current series feedback. Let us go further. Let us analyze the different elements of current series feedback. Let us analyze how the open loop gain is determined, how the feedback network gain is determined. Okay. So, now here we have drawn the AC equivalent circuit of an amplifier without feedback. So, the same circuitry which we have drawn previously, okay, is applicable here. So, input junction of a transistor base to emitter junction is represented by impedance is represented by HIE, RB is a biasing resistor, then collector current flows between collector to emitter, which is IC. Here you have RC also, and you are taking output across RC. That is very important here. You are taking output across RC. Now, how do you determine now the gain? Okay, from feedback point of view, gain, which is A here, can be expressed as parameter of interest here is output current, whereas voltage is applied here is at the input. So, gain A is equals to output current divided by input voltage. So, it can be calculated as minus HFE divided by HIE plus RE. So, how I naught is nothing but HFE into IB. So, you can observe that I naught is taken as positive if it is flowing into the load. Now, here the collector current is direction of collector current is, it is such that it is flowing outside the load. So, you have a minus sign here. So, it is minus HFE IB divided by what are there at the input? At the input you have HIE, which represents input impedance, as well as we have RE, right. So, we have RE also there at the input. So, we have RE here. So, HIE plus RE into IB will be the input voltage. IB cancels on the both the sides. So, you will get the open loop gain. Then the feedback network beta. So, you can calculate feedback network beta as Vf divided by I naught. So, why? Because this you can recall the concept. What is beta? gain here is beta is equals to Vf divided by I naught, feedback voltage divided by output current. So what is the feedback voltage here across Re? We are taking output feedback voltage is generated across Re. So it will be I naught into Re. The direction of I naught is negative to the emitter current. So it is called as minus I naught. It is in fact IE Re. IE is minus of I naught. So it is minus I naught Re divided by R naught equal to minus Re. So this is the gain of feedback network. Now the input impedance. Now this is the input impedance here. So you have calculated A, which is gain of the open loop amplifier. We have calculated beta, which is gain of the feedback network. Let us look at input and output impedances of transistor amplifier. Okay. So now what is there? Where is the input impedance is seen? Input impedance is the input impedance as seen from the input side. So what you can see from the input side, leaving the source, you can see RB and HIE being connected in parallel. I have also the feedback resistance Re being connected at the input. So considering this Re, effective input impedance becomes ZIE is equals to RB in parallel with HIE plus Re. So you have Re also there at the input with feedback. Okay, whereas what is output impedance? Output impedance is the impedance as seen from the load side. Okay, from the load side excluding load. So I can see only RC there. So Z0 will be equal to RC ohms. Okay. So this is how you can calculate input impedance is seen from the input side and output impedance is taken from output side. So now we are subjecting it to feedback. Okay, we are subjecting it to feedback. So we have already determined, okay, the input impedance with feedback, output impedance also with feedback of current series configuration. So what is the input impedance with feedback? ZIF is equals to ZI into bracket 1 plus A into beta. So we have determined this. AF we have determined already. ZIF is, okay, AF is what? AF, we have already seen the formula for closed loop gain. It is A divided by 1 plus A into beta. You have already determined A. You have already determined beta. So substitute both A and beta and you will get AF. So this is an expression for AF. So you will get AF as equals to A divided by 1 plus A into beta. Substitute A, substitute beta. So it will be minus HFE divided by HIE plus HFE RE. Okay, that is closed loop gain. Further, we have input impedance with feedback. So when it comes to feedback, I have to consider RE also, effect of RE. So that is ZIF. How can I express ZIF? ZIF can be expressed as ZI into bracket 1 plus A into beta. So 1 plus A into beta is nothing but the feedback factor. So after simplification, it can be arrived as HIE plus HFE RE. Okay, so these expressions are very, very important. And we have also determined output impedance with feedback, ZOF. ZOF here for a current series configuration, it is Z0 into bracket 1 plus A into beta. Okay. So these are very, very important. These are very, very important parameters. So you have determined closed loop gain, input impedance with feedback, output impedance with feedback. Even you can calculate voltage gain AVF. Okay, so voltage gain AVF is nothing but closed loop gain. So considering the only the voltage gain, we are calculating the only the voltage gain here. So which is V naught divided by Vs. You can calculate this as closed loop gain AF into RC. Okay, so this is how you can calculate. Okay, so now just come back to the slide. Okay, so we have closed loop gain AVF equal to V naught by Vs. You can, how you can calculate V naught? V naught is output voltage. So the output voltage is output current into output resistance. So which is I naught into RC divided by Vs. So I naught by Vs we have already calculated. It is nothing but closed loop gain AF. So substitute here into RC. Okay, so this is a parameter. So what all we calculated in current series feedback? We calculated A, we have calculated beta, we have calculated AF, we have calculated ZIF, ZOF and AVF. Fine. So you can solve one small problem, you can note down this problem, you can solve it, you can substitute the elements. Okay, so supply VCC, a 470 ohm resistance, a feedback. So this is a base resistance, you have collector resistance, emitter, input voltage is given as 10 millivolts, HFE and HIE are given to you. So on the board, okay, I have given the expressions. Okay, you have to just substitute in these expressions and you will get the element voltage gain. You can calculate as AF into RC. Fine. So this is how you can calculate this current series feedback configuration. Okay, so we have discussed now the voltage series feedback, one example we have discussed. Then we have discussed current series feedback, one example we have discussed. Okay, now we will proceed further. Voltage shunt feedback using op amp. Okay, recall this diagram, take down this diagram. Okay, so it's a voltage shunt feedback configuration. What all elements involved here? You have an open loop amplifier, you have a feedback network, an output and a source signal. Okay, so you have output resistance RL and a source signal. Now here for voltage shunt feedback, when we are mixing the voltage in parallel, we are substituting voltage source by the current source. So you have a current source IS here. Okay, so difference between this input current and the feedback current will give you the current II, which is given as an input to the amplifier. So you will get A equals to V naught divided by II, so which is observed at the output. So this output voltage is fed back to the feedback network. Feedback network collects or it generates a feedback current which is in proportion to the output voltage. This is mixed in parallel. So what is II here? II is difference of IS and IF. II is equals to IS minus IF. So how the feedback is brought in here, or how the stability is ensured? If output voltages increases or decreases from its nominal set value, the feedback current will also increase. If feedback current increases, which is drawn from the supply, then the input current decreases. If input current decreases, again the output voltage will decrease. So this is how you have a feedback here. This is how feedback happens here in case of voltage shunt feedback using op amp. Okay, what is an example here now? What is an example? The most important example which you will be coming across all electronic circuits is voltage shunt feedback. Okay, so this voltage shunt feedback topology, which is op amp is used everywhere. Okay, in all electronic circuits, you will be later in the next semesters you will be coming across this op amps. So this is used everywhere. So what is being followed is voltage shunt feedback here. Okay, so you can note down this diagram. So this is a op amp being connected in a inverting amplifier configuration. So this is the input voltage Vi. You have a resistance R1, you have a resistance R0. R0 is a feedback resistor here, which is connected between output and the input. So it acts as a feedback resistor. It is connected between the output and the inverting terminal. Okay, then the non-inverting terminal is grounded here. This input voltage V1 is replaced by the current source. It is now the equivalent circuitry. For our analysis of voltage shunt feedback, we are replacing input voltage source by its equivalent current source. So this current source will generate a current of magnitude V1 by R1, same magnitude. Okay. Then you have current II, which is the input current entering the op amp. So this is the op amp configuration. Non-inverting terminal is grounded. Output is applied to the input via feedback resistance R0, and you have an output voltage V0 here. Fine. So now let us see how the elements are controlled here. Very simple here. So output voltage is fed in parallel with the input voltage. So if at all output voltage increases, then the feedback current drawn will also increase. So the input current decreases. That is how the stability is brought into. Now let us look at the parameters of the voltage shunt feedback. Open loop gain A is equal to, now it is an op amp. We know that open loop gain of an amplifier is infinity. Op amp, open loop gain is infinity. Feedback network, it is IF divided by V0 will be minus 1 by R0. AF, closed loop gain. Now here in case of the op amp, the product, we know that AF is equals to A divided by 1 plus A into beta. The product A into beta is much greater than 1. So this AF will be, can be approximated as 1 by beta, because this can be further substituted as A divided by A into beta. A cancels. So AF can be put as 1 by beta. So 1 by beta is nothing but we have already calculated the beta. So it will be equal to minus R0. Substitute, you can get voltage gain also. Okay, so voltage gain with feedback AVF is minus R0 by R1. Okay, so this is used, or this is designed, simple design. You can achieve required voltage gain by adjusting the feedback resistor and the input resistance. You can achieve any gain. So it is minus R0 by R1. See, you can see if you adjust these resistances, if you adjust this R0 as well as R1, you can achieve any kind of desired gain. You can achieve that. Okay, now the whatever example FET we have discussed about voltage shunt feedback using op amp we have discussed. Now the same concept we can carry over to the FETs also. So this example is voltage shunt feedback using field effect transistors. So what the circuit arrangement consists of? Circuit arrangement consists of an input voltage source Vs, resistance Rs, okay, which is the resistance of the source. RF is very important here. RF is a feedback resistor which is connected between the input and output here. So you have supply source VCC, a drain resistance RD. You can observe that we have not given any value to this resistance. This simply because this gets bypassed via capacitor, because capacitance acts as a short circuit for the AC signals. So, during amplification, AC signal will prefer the path of the capacitance, because that being the low impedance. So, it will get short circuited, or this resistance is ignored in the calculations of feedback. Okay. Now, according to what we have discussed in the topology, input voltage source is first represented as a current source. So, it is represented by Is in parallel with Rs. The feedback resistance Rf is present between output and the input. So, it is present between these two elements. So, you can see that what is the input current II here, which is a difference of Is and If. So, feedback current flows through Rf. For AC analysis, this is nothing but the AC equivalent circuitry. When it comes to AC analysis, all the DC conditions are set to 0. So, here DC source is being set to 0. Okay. So, DC source is being set to 0, then you have a output resistance RD. Okay. So, this is the AC equivalent circuit. We have already seen in the starting units, first units, we have seen first sessions, initial sessions, early sessions, FET we have analyzed. Okay. You all have analyzed in the earlier modules. Okay. We will just continue that. Okay. Without feedback, what is the gain? Gain is V0 divided by II. So, this is FET. FET in II is the input current, output voltage is V0. So, we have already calculated this. It can be approximated as GM into RD into RS. And with feedback, the gain can be expressed as -1 by R0, IF divided by V0. Okay. What is the job of feedback network here? Recall feedback network. So, it generates output current in proportion to the input voltage. Input voltage for this is output voltage, right. So, we can just substitute that here, IF by V0. V0 can be put as minus IF RF, because it is a feedback voltage across the resistance RF. So, IF cancels, -1 by R. Substitute, you will have a AF, the closed gain expression, which is V0 by Is, which is equal to A divided by 1 plus A into beta. So, you can simplify, you can obtain the expression for closed loop gain AF. Okay. You can further evaluate closed loop gain with voltage as a parameter. So, AVF is V0 by Vs. V0 by Vs can be rearranged as V0 by Is into Is by Vs. So, further substitute, you will get the expression for closed loop voltage gain AVF. So, voltage gain is very important in voltage amplifiers. So, this is a parameter of interest in voltage series feedback also, as well as in current series feedback, voltage shunt feedback also. Okay. So, we have calculated AF, we have, this is a FET circuit. So, we started with this FET circuit, we replaced its small signal equivalent circuitry. Okay. Then we have calculated the parameters A, beta, AF and AVF, right. So, now calculate one small problem. Okay. So, for which relates to this, you can note down this problem, you can solve this. Calculate the voltage gain with and without feedback. Okay. For the circuit with the values, transconductance GM equals to 5 milliseconds, RD equals to 5.1 kilo ohms, RS equals to 1 kilo ohms, and feedback resistance RF is equals to 20 kilo ohms. So, use these elements. So, very simple, we have already derived. So, you calculate first from this circuitry, this is the given circuitry. From this given circuitry, you have to first draw the small signal equivalent or AC equivalent circuitry. After drawing this AC equivalent circuitry, you have to calculate A, beta, AF and AVF. Okay, so then you can solve this problem. Okay, so now we have one more topology, the last topology, the current shunt feedback topology. Okay, so recall the diagram here, current shunt feedback topology. So here input source is replaced by the current source Is, the open loop gain A is equal to I naught by II, feedback network beta is equals to IF by I naught here. So the amplifier is there, feedback network is there, and a current source is there. So the output current is tapped in series and it is mixed in parallel with the input current source. So the how the stability is being brought in here, basically the stability is being brought in by so feedback network. How? See, if this output current varies, then the feedback current drawn by this feedback network will also vary from the input. So suppose if the output current increases, then the feedback current accordingly increases and current flowing into this amplifier will decrease. That will again bring back the output to the same value. Okay, so this is how the current shunt feedback topology works. Okay, so you can take down this diagram first. Later on we are going to apply it to the circuitry. Okay, so fine, this is a current shunt feedback. So we will again discuss this current shunt feedback. We have one practical circuitry to be discussed, but before we do this, we'll take this current shunt feedback in the next session. Okay, so before we do this analysis, we have a recap. We'll have a recap of what all we have studied. So to start with, we discussed about example of voltage series feedback, right? So we discussed an example of voltage series feedback considering emitter follower as the circuitry. We analyzed A, we analyzed beta, we analyzed AF, we found out voltage gain with closed loop voltage gain also we calculated. Okay, so this circuitry emitter follower has a less voltage gain, but it brings in stability to the circuitry. Okay, then we discussed about current series feedback. This is used in all the common emitter configuration. Remember that CE transistor amplifier is used in all the circuitries. So we have used the CE amplifier here. Okay, so in all the circuitries we have almost all the electronic circuits employ CE configuration because it is having high current gain and high voltage gain. Here also stability is brought by the resistance RE. Okay, so this employs a current series feedback topology. Then we also discussed about voltage shunt feedback. Op-amp is the best example. In the coming semesters, almost all electronic circuits make use of op-amp. This is op-amp being connected in an inverting amplifier is an example of voltage shunt feedback, whereas op-amp being connected in non-inverting configuration, we have seen this, it is an example of voltage series feedback topology. Okay, so it is, we have already used these amplifiers, we have already used transistor amplifiers, FETs, but we have not looked at it from feedback point of view. So here we are looking from feedback point of view. Okay, so next we will again continue in the next session with current shunt feedback topology. Okay, thank you. So